Hi everyone, my name is Yiyue, the first year PhD student in CSRC supervised by Dr. Valeria Barra. And the project I'm going to present today is the 3D cardiac strain imaging of the left ventricle. As we all know, myocardial deformation provides priceless information for diagnosing cardiac diseases. The left ventricle is the most crucial part. While 2D strain imaging has been successfully implemented with well-established methods such as block matching and speckle tracking, 3D strain imaging still needs a lot of work to do. For example, for researchers especially, the 3D version poses significant challenges due to its high computational demands. And meanwhile, the majority of the commercial probes are generating 2D images instead of 3D. And also with restrictions in bandwidth, 3D hard images are often with qualities much lower than 2D. So in this project, we're going to work on 2D B-mode images, but generating 3D strain results. And as you can see in the flowchart, we first obtain 2D images from 3 different views from heart, which you can just regard them as X and Y and Z. Of course, they're all perpendicular with each other. And then a segmentation algorithm has been applied here, and we can have the segmented area of the left ventricle. And then finally, we derive the 2D displacement vectors in segmented areas using the block matching algorithm. Block matching is an algorithm that compares the brightness similarity of the two blocks. And through this way, we're able to establish a strain vector mapping. These vectors are then being processed and then mapped onto a 3D left ventricle model. And furthermore, principal component analysis has been applied here as well to enhance both the smoothness and accuracy of the displacement vector field. In this slide, you can see that there are 3 images in the first row, which shows the segmented areas of the left ventricle from 3 different views, and the 3 images from the second row shows the vector mapping results. You might also find out that all of these vectors looks very smooth. And the block matching itself, of course, cannot directly generate such smooth results. It was the principal component analysis that helps. And before we dive into the logic of a PCA, we need to know that block matching produces errors. For example, while 2 very different blocks have nearly identical sum of absolute different values, the block matching algorithm fails. So here's the logic. Specifically, we measure the displacement vector of a given block for multiple times using different algorithm parameters, for example, the block size and a lot of different parameters. And most of the vectors will point in a very similar direction, while a few outliers may deviate significantly, as you can see in the left figure. And then we will amplify these vectors by a different amount of scales. So their endpoints lies linearly, in a very specific direction. And then PCA will give us this direction. So that means we successfully get rid of the outliers. Now is the final step, right? To organize all 2D vectors and project them onto a 3D model. And it can be separated into 2 sub-steps. Firstly, we have to find a transformation matrix that links the pixel or the block's positions in the images and the points in the 3D model. And here we use the Procrustes analysis, which is a method that compares the similarity of the 2 shapes and then generate the transformation matrix. Here, of course, one shape is the segmentation area and another shape is the 2D slice of the 3D model. And the second step, since the transformation relationship has already been established, each point in the 3D model receives 3 different vectors from 3 views. And an optimization method has been applied here to generate a 3D vector that contains the most information from 3 different views. The right figure just gives us a very simple example of projecting one PSAX slice onto the model. So overall, this project introduced a very novel method to construct 3D smooth left ventricle strains from a 2D B-mode images. The robustness of the 2D block matching algorithm has been enhanced by applying principal component analysis method. The workflow in this project is particularly beneficial for researchers who is developing customized probes for strain imaging visualization. Future work will be focused on calibration between different views to make this algorithm better dealing with a wider range of B-mode images.